Have you ever wondered how laser lights work? This fascinating world of light and energy operates on the principles of laser technology. The term laser is an acronym for light amplification by stimulated emission of radiation. It may sound complex, but the concept is quite straightforward when broken down. At the heart of laser lights are several key components. First, we have the gain medium, a material that amplifies light. It could be a gas, a liquid, or a solid material. Then there's an energy source, used to excite the atoms or molecules within the gain medium, a process known as pumping. The energy source could be anything from a flash lamp to an electrical discharge or another laser. We also have spontaneous and stimulated emission, processes through which photons are emitted and light is amplified. Lastly, we have the feedback mechanism and cavity resonator that shape the laser beam. Stay tuned as we delve deeper into each of these components. First up, we have the gain medium. The gain medium is pretty much the heart of the laser light operation. It is this material that amplifies light, and it does this through a process called stimulated emission. Now, you might be wondering what kind of material can do such a thing? Well, it can be a gas, liquid, or solid-state material. For instance, gases like helium, neon, or argon are commonly used as gain media. On the other hand, we also have solid-state materials like crystals that serve the same purpose. Each type of gain medium has its own unique properties and contributes to the specific characteristics of the resulting laser light. In essence, the gain medium is like the fuel that powers the laser light. Without it, there would be no amplification of light, and hence, no laser. So that's the gain medium, the first key component of laser lights. Next, we discuss the energy source. This component of a laser light system is a critical ingredient. It's like the fuel that powers the engine. The energy source provides the necessary power to excite the atoms or molecules within the gain medium. This process, known as pumping, is vital for starting the laser light operation. Imagine a party where the music is the energy source and the people are the atoms. When the music starts, the people or atoms get excited and start to move. In the same way, an energy source gets the atoms or molecules in the gain medium excited and moving to higher energy states. Different energy sources can be used for this purpose. Some lasers use flash lamps, while others use electrical discharge. There are even lasers that use another laser as their energy source. Each source has its unique characteristics, making them suitable for different types of lasers. And that's how the energy source plays a crucial role in laser lights. Now let's talk about spontaneous and stimulated emission. Picture this: atoms or molecules in the gain medium soak up energy and ascend to higher energy states, but they can't stay there forever. Sooner or later, they'll return to their lower energy states. When they do, they emit photons spontaneously. This is what we call spontaneous emission, the natural emission of light. But there's another player in this game: stimulated emission. This is where things get really interesting. Here's how it works. A photon collides with an excited atom or molecule in the gain medium. This collision prompts the excited atom to release a second photon. But this isn't just any photon, it's a clone of the first, identical in energy, phase, and direction. This process is what leads to the amplification of light. These emissions are fundamental to the operation of laser lights. Moving on, we have the feedback mechanism and the cavity resonator. The feedback mechanism is an integral part of laser technology. It's the magic trick that turns a simple light into a coherent and focused beam. Picture this: you've got a gain medium filled with excited atoms all ready to emit photons. But we don't want these photons just flying off in any direction. We want them all moving in the same direction, creating a beam of light. That's where the feedback mechanism comes in. At either end of the gain medium, we have mirrors. One mirror is highly reflective, bouncing back nearly all the light that hits it. The other mirror, however, is only partially reflective. It lets a small portion of light pass through. As the photons bounce between these two mirrors, they stimulate further emissions from the excited atoms, amplifying the light. Now, let's add the final touch: the cavity resonator. This is the space between the two mirrors. As the photons bounce back and forth, they create standing waves of light. These waves build on each other, enhancing the coherence and directionality of the laser light. The cavity resonator and feedback mechanism work together like a well-oiled machine, ensuring that the photons emitted by the gain medium are amplified and directed into a concentrated beam. These components help shape the laser light into a concentrated beam. Finally, we arrive at the laser beam itself. The culmination of this intricate process is a concentrated beam of light. It's narrow, intense, and impeccably focused. This beam is characterized by the properties of the gain medium and the design of the optical cavity. Picture a beam of light that's so coherent, it can maintain its narrowness over vast distances. That's the beauty of a laser beam. But lasers aren't a one-size-fits-all phenomenon. There are different types, each with specific applications. Let's take a quick look at some of them. First, we have semiconductor lasers. You'll find these in places like CD players or fiber optic communications. They use a semiconductor as the gain medium and are known for their small size and low power consumption. Then, there are gas lasers. Remember the helium, neon, or argon gases we talked about earlier? Those are used in gas lasers, which are popular for their efficiency and the high quality of the laser beam they produce. Last but not least, we have solid-state lasers. These utilize a solid gain medium, often a crystal. You'll see them in a variety of applications, from industrial cutting and welding to medical surgeries and even in your everyday laser pointers. And there you have it, the fascinating world of laser lights, from the gain medium to the final beam. Let's recap what we've learned today. Laser lights operate based on the principles of laser technology, which include key components such as the gain medium, energy source, spontaneous and stimulated emission, the feedback mechanism, and cavity resonator. These elements work together to produce a concentrated beam of light with specific characteristics. Different types of lasers are designed for various applications, each with its unique properties and operational principles. Thank you for joining us on this enlightening journey into the workings of laser lights. Until next time.